and welcome to this video walkthrough on an enthalpy past paper question. Now there's quite a lot to read on this one, so let's start having a look. A student carries out an investigation to find an enthalpy change for decomposition of magnesium carbonate, and this is this equation here. This enthalpy change cannot be found directly, it can be found indirectly from the reactions below. We've got a Hess cycle here, and we're given some experimental data which we can use to calculate enthalpy change 2, and we're given a value for enthalpy change 3. So the question says use the student's results to calculate delta H2 and then calculate a value for delta H1 using the Hess cycle, which includes delta H2 and delta H3. If we start with our Hess cycle first then, and we remind ourselves what Hess said, he said that the energy to go via route 1 is equal to the energy to go via route 2. So we've got two different ways of getting from magnesium carbonate to these products. We can go this way or that way. And how do we know those are the two routes? Well, this one, we are following the arrows clockwise. So that's one of the routes, and the other one, the arrow is going against those other two arrows. It's going anti-clockwise, so that must be part of another route. Now, since these two routes are equal, it doesn't matter which we call route 1 or route 2. The purple route could be route 1 or 2, doesn't matter. I'll call it route 1, and this one route 2. So I want to know what the expression is to calculate this delta H1 then. First, I'm going to collect my terms involved in this purple route 1. So we've got delta H1 plus delta H3, and that is equal to route 2, which just involves delta H2. Now we're trying to calculate this delta H1 from the other two. So I'm going to rearrange in terms of that. Leave delta H2 where it is, and this one is going to move across the equals, so it will change its sign. It will become minus delta H3, and this is what we can use, this expression, after we've got our number for a value for this one. Now, what if we weren't given a Hess cycle for this question though? How would we come up with this expression then? Because there are past paper questions like that where they'd ask you to do the same thing, but there'd be no Hess cycle, and we'd have to look at these equations, so the clues in the equations. So I'm going to show you how to do that next, because there are exam questions like that that exist, so it's well worth knowing how to do this. So we want delta H2 and delta H3 equations to add up to give delta H1, this one. So somehow we have to combine these two equations so that together they match this one. How do we do that then? So we can see we've got magnesium carbonate on the left, and so does delta H2. We've got some extra things like hydrochloric acid that we need to get rid of, and water as well. If we look at the right side of this delta H1, we've got magnesium oxide. That's not present in delta H2, but it's over here in delta H3. We need it on the right, so we are going to reverse delta H3. So if I write these out then, we're going to keep delta H2 as it is, the equation. So if you're not here for this bit, just skip past this bit, but it is worth knowing how to do this. And then I'm going to reverse this delta H3 now. So the products over here are going to become the reactants, and you'll see why soon. And then these reactants will become the products. Okay. So that's delta H2, that's delta H3. And remember, the goal is to add these, combine them, and make them equal to this. We want to match this equation. Now, anything that appears on both the left and the right side of the arrow, we can cancel it out. We can get rid of it. So we can see we've got magnesium chloride that's on the right and the left of the arrow. That can cancel out. We've also got 2 HCl, and we've got 1 water. What are we left with then? we're left with magnesium carbonate decomposing to magnesium oxide and CO2, which matches delta H1. And you might be thinking, so what? How does that help? Well, that helps us write our expression. So we've made delta H1, so that equals delta H2. And what did we do to this equation? We reversed it. So we put a negative sign to show that we reversed that equation. So minus delta H3. And we can get the same answer that way if we weren't given the Hess cycle and we got stuck. What next then? So let's have a look at these results to get this. Let's have a look at these experimental results then. So here's the method, and we're reading through, picking out the key things, and we've got a results table here as well. So they weighed the polystyrene cup, they weighed the cup with the solution. Now we need to, in order to find an enthalpy change, delta H1, we need to use the equation Q equals mc delta T, and we have to find Q first, which is energy, before we can convert it into energy per mole. So to get M, we're going to subtract these two. The difference between these will be the mass of the solution, and that is the mass that we use in the equation. So it says the student added 100 centimeters cubed, which should equal 100 grams, but this is a more accurate way to get the actual mass that was used. And then we can subtract the differences between final and initial temperature, and we get our temperature change. And then we know that C is a constant in that equation. So if we plug in our values then, we can work out an energy value in joules, 2152.9 joules. Now there's two things that we could work out the moles of. We could work out the moles of the hydrochloric acid because we've got a concentration and a volume. It does say this is in excess though. Or we could work out the moles of the magnesium carbonate, which isn't in excess. So which one do we work out the moles of? Well, it's always the limiting reagent. It's never the one that's in excess. So we're going to work out moles of this by doing mass over MR. So if you were doing this exam question, you would write in the answer box. I'm just showing you how we'd go about getting the answer. So mass over MR, so 4.215 over the MR, which is 84.3. Let's see what we get, 0.05. Okay, let's get delta H2 then from this data. So delta H is Q, and we want to convert that into kilojoules, so we're going to divide by 1,000 over moles. So 1, 2, 3, so 2.15, I'm going to round that, 3 over moles. 43.06 kilojoules per mole. We can see that the final temperature was higher than the initial temperature. In other words, we had a temperature rise in that reaction, that delta H2 reaction, which means it was exothermic. If the reaction's exothermic, we have to stick a negative sign on our delta H value. Very important. If we don't, it won't give us the correct answer. So when we come over here then, we can find and calculate delta H1, and we can do that by using our equation that we figured out earlier. So we pop our delta H2 here and we subtract from it delta H3, which is given to us. So it becomes a minus minus, which will give us a plus. Pop that in the calculator and we get 93 kilojoules per mole. I hope that was helpful. If it was, please like and subscribe.